Good morning. It's a pleasure to participate in this 20th anniversary event. In this presentation, Claire Max, Bruce Macintosh, and I will all take turns in providing a perspective on the past, present, and future of Keck adaptive optics. I'll begin with, once I figure out how to go forward. Which one? This button? I'll begin with my perspective will focus on the AO systems themselves. Bruce will focus on planetary systems. And Claire will talk about extragalactic science and the impressive science gains to be had with our next generation AO system. So since we have a diverse audience, we thought we'd begin with why adaptive optics. In the 400 years since Galileo's time, astronomers have been building larger and larger telescopes in order to collect more light, to see fainter and more distant objects. And so the sensitivity of these telescopes has grown with their collecting area, or the square of their diameter, d. It's only been in the last couple of decades, however, that astronomers have been able to make any significant progress on reducing the size of the images obtained with these telescopes. So theta here. And the reason for that is that the turbulence in the Earth's atmosphere blurs the images we obtain with our telescopes. Okay? And so the role of astronomical adaptive optics is to correct for the Earth's atmospheric turbulence in order to achieve the theoretical diffraction limit of these telescopes. To illustrate this, here's an image of Neptune without adaptive optics. And it's limited basically by R0 here, the spatial scale of the turbulence, to be about 4 resolution elements across Neptune. And we turned our AO system onto Neptune back in 1999. This is what we saw. Instead, we're limited by the diameter of the telescope to about 40 resolution elements across Neptune. So how does adaptive optics work? The light from a star or science object is distorted by turbulence in the Earth's atmosphere. We collect that light from the telescope, send it off a fast tip-tilt mirror, off a deformable mirror, and then to a wavefront sensor and a science camera. We use the wavefront sensor information basically to figure out how much image motion there is, and we correct that image motion with the fast tip-tilt mirror, and then we correct the higher order distortions with the deformable mirror. This is done on scales of hundreds to thousands of times a second. So why laser guide stars? Well, natural guide stars are only available, that are bright enough, are only available over about 1% of the sky. So what we do is we create our own artificial beacon with a laser so that we can observe much more of the sky. We still do need a natural guide star to measure the image motion, but it can be about 100 times fainter. So let me introduce you to the Keck AO systems. On the Naismith platform of each Keck telescope, there's an AO enclosure. And in that enclosure, we have the AO bench, all the optical components that correct for the wavefront, and then send, that's about 8 foot by 8 foot here, and send the light to the science instruments, the near-infrared science instruments that Ian just spoke about. A near-infrared camera, an integral field spectrograph, a high-resolution spectrograph, and a dual swatter module that feeds the Keck interferometer. And then we also project our laser beacons from both telescopes. So since this is a 20th anniversary, I made a timeline of the last 20 years for Keck adaptive optics, beginning in 1993 when Ed Stone wrote a proposal to the Keck Foundation for the AO system. The next year, the Keck Foundation did fund our project, and we wrote our original design book, requirements book, Keck AO book.
These are very precious. You have to fight over them.
And 5 years later, we had first light, natural guide star system on Keck 2. And this is a happy team about 4 in the morning on the summit drinking champagne. So this is what the Galactic Center looked like to us before adaptive optics. This is the central 0.8 by 0.8 arc seconds of the Galactic Center. Later in 1999, we closed the loop on the Galactic Center, and this is what we saw instead. So lots of stars on which Andrea could start to work. And then in 2001, we commissioned the Keck 1 natural guide star system. And we also added NIRSpec and NIRC2 as science instruments behind the AO system, as well as the interferometer. In 2003, we started with the Keck 2 laser guide star system. And by 2004, we were doing science with it. here's that same central arc second around the supermassive black hole at the center of our galaxy, and many more stars can be seen here. OSIRIS was added in 2005. We did a wavefront controller upgrade in 2007. This is an image at J-band 1.25 microns of a brown dwarf binary before the upgrade and after the upgrade. So we continue to upgrade the AO capabilities. And then just last year, we started doing science with our Keck 1 laser guide star system. So the science productivity of the Keck AO systems has been good, and it continues to grow. This is the number of refereed science papers by year. About 3 papers were published in 2000, but now we're up to about 60 papers per year in 2012. How are we doing versus our competition? This is a plot of those refereed science papers, now just for laser guide star papers versus year. And I want to make 3 points. One is we're dominating. 70% of these papers are from the Keck system. Another point is we got there first. Keck is a tradition of getting there first. And for laser guide star, we also did that. And the third is laser guide star adaptive optics is challenging. And you can see that by the fact that the competition is not yet being nearly as productive. So yes, we're doing great science. Hey, but we can do a lot better. This is a plot of performance in terms of K-band STREL versus magnitude of the natural guide star. This is a perfect image, if we could do that. And what we instead get, even on a bright natural guide star, is this kind of image with a STREL of about 50 or 60% of the perfect image. And as we use fainter natural guide stars, the image starts to degrade. At some point, we find laser guide star does better and allows us to go to use much fainter stars and therefore much higher sky coverage. Okay? And this is how the performance goes versus wavelength. This is at 2 microns. We get a STREL here in this image of 0.6. As we go to fainter or shorter wavelengths, like J-band at 1.25 microns, the STREL has dropped, but you might also notice that the angular resolution has improved. These examples are for typical seeing conditions nearer the zenith. The normal science case is, astronomers are always challenging us, so the normal science case is much more difficult. Here's an example of a science case observing a brown dwarf binary, one of Mike Liu's targets, with a fainter natural guide star, off-axis, 30 arc seconds, and observing over at 50 degrees zenith angle. So these are the sort of error budgets we use to drive our development efforts. Okay? So these are all the error terms that contribute to the degradation of the image. So we focus on the biggest terms. So for example, the bandwidth of measurement errors for image motion, bandwidth of measurement errors for higher order. And so what are we doing about it? We're improving our laser guide star beacon, and we're improving our tip tilt sensing. Okay? And so we're using these kinds of error budgets to also drive our next generation AO system. And these components I'll talk about are part of that next generation AO system as well. There's other aspects that impact the science performance. One of those is knowledge about what is the corrected image look like. How much of it is due to the science object, how much of it is due to the residual atmospheric turbulence and aberrations of the system. And so we're also developing a point spread function reconstruction capability. And I'll talk about all 4 of these items in a minute. Starting with laser launch. So currently we launch the Keck 2 laser from the side of the telescope. What you're seeing here is basically scattering from atoms and molecules in the lower atmosphere. What we actually use is this spot up at the top here. Re-emitted photons from the sodium atoms up in the mesosphere, up at 90 kilometers. To see the impact of elongation here, we project from this side. What we've done here in this image, unstacked the 36 segments of the Keck telescope. And close to where we project from, the images are round, but as you get further away, they get more and more elongated. And that's because the sodium layer actually has some thickness to it. It's about 20 kilometers thick, and so we're getting a perspective elongation. So our solution to that is to launch from the center of the telescope instead, and in this case, the images are about half the size. Another improvement we're working on is replacing the dye laser, which is pretty old technology developed at Lawrence Livermore National Lab, with a fiber laser. The dye laser consists of 6 pump lasers and a dye master oscillator on the dome floor in a room down here, and then 2 stages of dye amplification on the side of the telescope. And overall you'd have about 50 kilowatts of power coming out of the wall and 15 watts of laser power going to the sky. So we want to get a little more efficient. So the new laser we're working on is much smaller. It's 0.7 meters here. It fits on the side of the telescope here. There's actually room for 3 of these lasers for our next generation AO system, although we'll implement 1 to start with, and then just a support electronics rack. Okay? So in terms of wall power, now we're down to 2 kilowatts. In terms of return from the sodium layer, we're up by a factor of 10 just in the type of laser it is, because it's continuous wave versus pulsed. What's the benefit of that? Another example, we're always showing Andrea's pretty pictures, but Andrea's been following the orbits of these stars around the supermassive black hole at the center of our galaxy. Here's a simulation of our current performance, and here's what we expect in terms of improvement. A factor of 2 in that Strel ratio. We're also working on doing our tip-tilt sensing in the near-infrared. Currently, we track on the visible image, which is limited by turbulence in the atmosphere. So we've got this big blob we're trying to track on. But in the near-infrared, we've got a partial correction of our natural guide star. So instead, we'll track on this core here. In addition, the stars are generally a fair bit brighter in the near-infrared than in the visible. And what sort of performance improvement do we expect? Here's the RMS tip-tilt error versus sky coverage. Our current performance is this blue curve, and we expect to move to a much better tip-tilt correction and also much higher sky coverage as a result. And this is allowed now because the IR detectors have improved. We can read them out faster, and they have reduced noise. That's the camera we're building for this. The final development project I'll talk about is the point spread function determination. So the issue is that our AO-corrected image is changing with time, it's changing with position in the science field. Our goal is to provide the astronomers with a real-time estimate of that point spread function. And they can use that to improve the astrometry, the photometry, the understanding of the kinematics of the science observations they perform. We've had to do a couple of hardware additions to support this. One is to have improved telemetry from our AO system, which we use for this reconstruction. And another was to add an atmospheric profiler on the summit of Mauna Kea. There's 2 efforts going on here. One is to understand the off-axis PSF as you move out in the field. And that's an effort led by the UCLA group. And here's a plot of Strel ratio versus time. And this red curve is basically an off-axis PSF, or star. And the green is how well we are able to estimate that PSF. Okay? The other project we're working on is to estimate the on-axis PSF. This is an actual star image. This is our reconstructed point spread function using AO telemetry and on-sky phase diversity. And here's the difference. And we're trying to also understand how that difference affects the astrometry, photometry, etc. In my final slide, I wanted to appreciate all the elements of the success of the Keck AO systems. Beginning with, I've had the privilege of leading the AO development efforts and working with a lot of talented and dedicated engineers that have made these systems a reality. We wouldn't be doing cutting-edge science, of course, if we didn't have great instruments to go with the system, as Ian just discussed, those near-IR instruments. We've had to work with vendors to build a lot of the components that go into these systems. Science productivity depends on our observatory operations team, operating these systems efficiently and well every night. And finally, we wouldn't be able to do, or not finally, but we wouldn't be able to do any of this without funders rising to the occasion to provide the financial resources to do this, beginning with the vision that the Keck Observatory had and continuing with other foundations and federal funding. And another key ingredient is a close collaboration with our science community and users that use the system both productively and creatively. Thank you. I'm going to pass the laser pointer to Bruce.
Thank you. I'd like to thank Peter for handing me the laser pointer and Keck for inviting me to give the opportunity to speak here. I was charged to talk about solar system science, both inside our solar system and extrasolar planets, and I'll do that, but I also want to talk a little bit about AO from my personal perspective, and then spend quite a bit of time talking about exoplanet imaging and spectroscopy at the end. And My personal perspective is that I've actually been part of the Keck community pretty much as long as there has been a Keck. I did my PhD at UCLA with Ian McLean and went straight from there to the adaptive optics group that Claire Max led at the time at Lawrence Livermore, initially to do AO observations at Lick Observatory, where we pioneered the laser guide star techniques that Keck is still using and made our images of Neptune. But then starting to do science with Keck. So those who are familiar with Keck will recognize this picture is from a long time ago. Two key clues. First, I'm wearing a sweater, which means I'm actually observing on the summit, which none of us do anymore. And second, there's still some residual hair, which is no longer true. Picture that Barbara Schaefer took a very long time ago when we were standing up on the summit. In those early days on the summit, we actually, even before there was adaptive optics, were studying the planets of our solar system using techniques like speckle interferometry, where a movie, a series of very short exposures that freeze the atmospheric turbulence, are post-processed afterwards to produce near diffraction limited images of, in this case, Titan, a moon of Saturn, where you can see atmospheric cloud features at its southern hemisphere, and continents, highlands of bright rock and ice against dark organic material located on the surface. But really what we all came to do was work on the adaptive optics. And Peter showed this. I'm just going to show it again. The original blue book, the design study for the Keck AO system, was sort of handed to me by Claire pretty much as soon as I started working there. And I was fairly stunned by the document, and still am. I still hand out photocopies of this to new postdocs who come to work for me. It's 400 pages of really detailed analysis of how an adaptive optic system works, where even the equations that are needed to determine that didn't exist before these people derived them, wrote them down, and led to a system design that was designed to work, that was actually designed to do science, as opposed to throwing a bunch of components that you could buy off the shelf into it. And that philosophy has continued at Keck. To my biased mind, actually, the single most exciting slide Peter showed was the one that looked like a spreadsheet, the error budget for the Keck AO system. And that's exciting because no other observatory has anything like that. No other observatory understands the way their AO systems work in a way that has let them continue to design and upgrade and move on to the next generation of systems. And a lot of that has come as a collaboration from the AO people at Keck, as well as the scientists and engineers at other institutions at the universities and at Lawrence Livermore Lab itself. I think my last contribution in the very first days was I said, hey, let's turn the AO system and look at Neptune, because that'll make a pretty picture. So I can take some credit for the fact that Keck had this gorgeous early science light image of Neptune to put on all of our pictures since then, although I don't get royalties for it, unfortunately. I'm just going to show an example of a piece of solar system science, again, that highlights the strength of Keck and the flexibility we have. These are observations of Io. So most of you are familiar with Io. It's one of the moons of Jupiter, the closest to Jupiter, so it's tidally heated as it goes around in Jupiter's orbit, squeezing the interior and keeping the interior extremely hot and molten. So the surface is pretty much covered with volcanoes. On this island, if you build a house, the typical lifetime of the house before it gets wiped out by a volcano is about 200 to 1,000 years, depending on where you're silly enough to put your house. On Io, the typical lifetime, if you build a house, would be about 2 years before it would get wiped out by volcanic resurfacing. So people tend not to build houses there. We wanted to study these volcanoes, but we're limited in images. This is a Galileo visible light image. The volcanoes are visible, but you can't really tell much about them because, of course, there's a lot of sunlight mixed in. In infrared, you could see the volcanoes, but at short infrared wavelengths only if the sunlight wasn't there. And so we observed Io during eclipses. Here's the sun, here's the Earth, here's Jupiter's shadow. And during an eclipse process, Io passes into Jupiter, but if the Earth is suitably elongated from the sun, you can still actually see Io, and you can see the volcanoes get highlighted. The problem is when it passes into Jupiter's shadow, there's no light left over for the AO system to lock onto. And so we actually lock the AO system onto another moon that happens to be passing in front of Io as the eclipse goes on. It's an incredibly challenging process to go through and really could only be done with a place as flexible as Keck. Here's movies Frank Marchese prepared for me. This is a visible light, what you would see from Earth. There's Io coming in. We'll start in a second or so, assuming the remote's behaving. And the other moon going by. And here's a near-infrared image. As it passes into the shadow, all the sunlight goes away as the Terminator walks across it, and we can see the glow coming from the individual volcanoes on Io's surface at a resolution that's actually higher than that provided by the Galileo spacecraft, even though the Galileo spacecraft sort of cheated by being right out there to do its observations.
In the infrared.
In the infrared. Over the course of these decades, as Peter said, the Keck performance has been improved, and the planetary images are a good way to show that. For example, Uranus from 2000 to 2004, as upgrades were made, analysis of the performance led us to understand what was going wrong. People like Marcos van Dam and David Lemignon tuned the AO system. The images became so much sharper, you can see multiple details of the individual moons. Keck is actually powerful enough it caused Uranus to tilt over on its side, too, so that we could see more detail in the southern hemisphere. Similarly, on Neptune and Titan, we can see details on the surface that we could never imagine before. So the second part of my talk, I'm going to hijack. It always sort of irritates me when people are asked to give review talks and they talk only about their own group science, but I'm going to do it. Partially because almost all the other science by other groups is being covered by review group talks by other groups, and partially because we have some very exciting results that are appearing in Science today, coincidentally, that we can present here for one of the first times. This is the study of exoplanets, in particular of young exoplanets. Jeff Marcy will talk a lot about mature exoplanetary systems seen through Doppler techniques. What can be done with adaptive optics is studying planets when they're young, when they're still hot and glowing with the initial heat of their formation. This is an artist conception produced by artists working for the Gemini Observatory. Planets that are 30 million years old will have temperatures of, say, 2,000 degrees, bright enough that we can see them with our infrared astronomical techniques. Planets, this is a 2004 scatter diagram of extrasolar planets in massive and major axis space, the ones that were known through the Doppler techniques. The Doppler observations Jeff will talk about are immensely powerful. But to biased people like me, they're also a little frustrating because you never actually see the planet. You just see this little wiggle on a Doppler graph. You infer critical parameters about the planet. It has revolutionized our understanding of other solar systems. But it'd be nice to actually see them. We started trying to do that with Keck in 2000 in some of the very first observations, initially following up young stars that had been looked at by the HST NICMOS instrument. Here's a NICMOS image. This is a bright star. The star only occupies about a pixel or two. The rest is all scattered light, lens flare from imperfections in the optics of the Hubble Space Telescope in this case. The potential candidate planet is still visible against that lens flare. And here's a Keck image from 2000 showing we actually were as good at doing this even then as NICMOS was, and we could see this candidate glowing young planet. Of course, it turned out not to be an actual glowing young planet. It turned out to be a background star, but we could prove that through comparison of the NICMOS images. We went on with this idea of analysis of understanding. We looked at these Keck images. Here's a similar image where the star really only occupies a pixel or two. All the rest of this is scattered light. And we carried out analysis to understand how that connected, in this case, to the design of the Keck telescope, to the segments, to the aberration in the segments themselves. I should say, though these do come from aberrations in Keck, Keck is actually still the best telescope to do this with. The Keck primary mirror is better than any other telescope primary mirror for these purposes, but it's still not perfect. And each of these little blobs, these speckle artifacts, is much brighter than the planets we potentially want to see. And so we had to figure out ways to get rid of them. We took advantage of another design feature, not of Keck, but of the Earth, the fact that the Earth rotates. Over the course of a night, if you're standing if Keck had an eyepiece, which unfortunately it doesn't, and you watch something over many, many hours, you would see it rotate against the sky due to the rotation of the Earth. Normally that's countered. All of the instruments Ian and Judy showed you counter-rotate. DEIMOS, this enormous multi-ton thing, is on a bearing so that the whole thing rotates the other way to hold the field of view fixed. We turned those bearings off. I'm going to show a movie here. Here's another one of these high, massively overexposed images, taken in a mode when the image derotator is off, so that the artifacts that are part of the telescope will stay fixed on the detector. Anything that's real in the sky will rotate. And you can see moving between the little artifacts a real little dot, an actual object in the sky. And if you have very good eyes and you stare here, you can see another real little dot. We just went through zenith, so everything moved very rapidly, moving through the pattern. The middle image is the same series of images, 10-second exposures over the course of a couple of hours, with basically a weighted moving average of the static artifacts removed. And in that, you can easily see the two candidate planets. I can't see from this angle because the contrast is low, but one down here and one up here. And this image is the series of those now derotated in software and stacked together so that you can see the sum, in the end, a third planet becoming visible. And of course, this led to the images of the HRD 799 system, the first images of an entire extrasolar planetary system seen from outside, 3, and now we know 4 massive planets, 3 to 5 times the mass of Jupiter, hot, thousands of Kelvin temperature, but really planets. And you can watch over the course now of 10 years of observations of these and see these things orbiting around their star, just like Kepler's laws say they should. That was not an enormous surprise because we know Kepler's laws work. But actually seeing Kepler's law from outside is one of the most exciting things I've seen as a scientist. We want more than just the power of this is not just seeing the planets, but since we can separate their light from the star, we can use these spectrographs Ian was talking about to characterize them. We're using the OSIRIS instrument Ian talked about. Here's its field of view laid down on the image of the bright star. Here's the planet sort of detectable against the artifacts. But as Ian said, OSIRIS takes a spectrum of every field of view. And so I can turn this into a movie, stepping from short wavelengths to long wavelengths. The artifacts, because they're caused by diffraction, have a position that changes with wavelength. The planet's position doesn't, though its brightness does. And I can take advantage of that to remove the artifacts and see the planet. But of course, it's a spectrograph. We don't just see the planet, we get a spectrum. This was done first by Mike Liu and his student Brendan Bowler over a narrow range of OSIRIS information, but really the first good spectrum of an imaged extrasolar planet. Over broader ranges, Travis Barman, myself, and other collaborators took H and K band spectra. In those spectra, we see absorption from CO, a little bit of absorption from methane. We see spectra that are very different from the brown dwarfs that you'll hear about later, really the conclusive proof that these were planets that we were actually imaging. What we've done now is we've moved in one planet, HRD 799c, and we've improved our image processing a lot. C is much brighter. We spent more Keck time on it, and we did an even better job of removing the speckle artifacts to the point where now, in a paper that came out in Science Express today by Quinn Konopaki, we have spectra at the full OSIRIS resolution of a planet. This is the HRD 799c spectra. The black is a model, but the red line overlaid it is the spectrum. These are the elements you expect to see. Carbon monoxide, for example, you can see at full OSIRIS resolution the CO drop. This is the spectrum of water vapor. You can see individual water lines in this spectrum mixed in with the noise, conclusively seeing that there's water and CO present in the atmosphere. This is the spectra of methane. You can conclusively not see that there's any methane whatsoever in this planet, even though at these temperatures you would expect that to be true. That's occurring because there's circulation in the planet's atmosphere. Here's three-dimensional models of the structure of a planet's atmosphere. Jupiter, for example, has CO way deep in its interior where you can't really see it, thin clouds of ammonia up at high altitudes because Jupiter has a temperature of 100 Kelvin. 1,000 Kelvin brown dwarf, the objects we knew before we knew planets, have opaque clouds of magnesium and silicates deep beneath methane and carbon monoxide, so you see their signatures in its spectra. The planets, because their gravity is weaker, because their atmospheric structure is different, and because they're young, have almost no methane because the atmosphere circulates up and down, and the methane is pushed down into the hot interior of the planet where it's destroyed. The carbon monoxide is brought up from the hot interior, and the clouds are raised up to the point where they peak up above all of these absorption lines. And finally, with these spectra, we can measure ratios, abundances, and in particular, we can constrain the ratio of carbon to oxygen in a way that's very model independent by comparing the strengths of the CO2 lines to the H2O lines. And that matters because that tells us something about how the planet formed. So we think planets form in disks, that stars are surrounded by disks of gaseous material. The star has a ratio of carbon dioxide of about 0.55, which is the ratio of interstellar gas. That's what the disk would have if it was just a uniform mix. But it's not a uniform mix. In the outer parts of the disk, it's cold enough that ice can form, and so grains of water ice form and suck up a lot of the oxygen, leaving behind gas that's depleted in carbon to oxygen as a ratio of about 0.9 or so, going to even higher ratios as you go out in the disk. The planet also shows evidence of being depleted in oxygen at that same sort of level. The theory of how you form planets, at least how the planets in our solar system formed, is that these icy materials conglomerate to form an icy core, which then absorbs gas directly from the protoplanetary disk. But by the time it does that, a lot of those ices are gone. And so the disk has got a little bit of ice in it, but it's significantly depleted, the gaseous envelope, is significantly depleted of oxygen. That's what we see as the signature in this planet. At about a 2 sigma level, its carbon to oxygen ratio is different from the star, showing that it formed through this process of core accretion, the process we think formed the planets in our solar system. So the perspective, sort of personal and scientific, I think a great strength of Keck, especially in this adaptive optics field, has been the collaborations through the NSF Center for Adaptive Optics, through the long-standing relationship with Lawrence Livermore. Scientists and engineers at a lot of institutions have kept working to keep the AO system competitive and to understand how it works. And Keck really is the dominant adaptive optic system, as Peter said, on the 8 to 10 meter telescopes in the world today. We also dominate the field of direct exoplanet detection, producing images like this and characterizing them, though that's not going to be true forever, and instruments are being prepared for other observatories that will be competitive. But the next generation AO system should help Keck remain as a leader in this field. So let me pass this on to Claire.
So I, too, will talk a little bit about history of the AO and laser guide star concepts and their history at Keck. I'll talk about extragalactic science accomplishments with Keck AO up to today. And the purpose of that is to be proud of what we've done, but also to whet your interest in a possible planned new next-generation AO system. So let me go back here. AO history is really interesting to me. It has, because of the interweaving of advances in technology between the military and astronomy communities. So it was suggested by an astronomer, Horace Babcock, in 1957. His ideas were all fine. The problem was the technology wasn't ready. For example, his deformable mirror was a flat piece of glass with an oil layer, and the thickness of the oil layer was to be varied by electrostatic forces. And that just wasn't going to work. And now we have much better technology. In the early 80s, lasers were first used to measure the turbulence in the Earth's atmosphere. These were classified experiments with green lasers. And the point was, in Star Wars, they wanted to be able to project lasers to shoot things down and also to take images of what was up there. The Russians at the time were launching a satellite per day, and one wanted to know what these things were. And in many, many, many cases, we had no idea. So taking a picture of them seemed like a good idea. And then in the early 80s also, the Jason group, which I belong to, suggested, well, green lasers for various technical reasons might not be as good as using a yellow sodium layer laser guide star. And that report was classified. It was declassified, as I'll tell you, in 1992. But that was the start of the concept of using a yellow laser to excite sodium atoms up at 100 kilometers altitude in the atmosphere, which is the dominant technology used today. So a little bit more AO history. Right after that, some astronomers who knew perfectly well that there was a sodium layer in the Earth's atmosphere, and they knew about the sodium ground state transitions, published 2 papers in the open literature. They didn't know anything about the classified work, and so, quote, the secret was out. And that led immediately to the declassification of the military work in 1991. Not quite immediately. A lot of us pushed for a while to make it happen. There was a very famous meeting of the American Astronomical Society, which I remember to this day, where Bob Fugate stood up and talked about the classified work. Charlie Towns was one of the people who organized the meeting. And when the results were announced from the military lasers, you could sort of see the shockwave propagate back through the audience. Then in 1992, at Livermore, we had a lot of lasers, and one of them in particular could be tuned because it was a dye laser. So we tuned it to this yellow sodium wavelength. And we had this amazing / ridiculous experiment. This is an office building in the middle of the Livermore site. This is a tree, and this is a tent that we set up. And we took one of the laser beams that was coming underground and turned it upwards, retuned it to this yellow light, and showed that you could actually measure the wavefronts, measure the turbulence in the atmosphere at the required rates. And that gave us the confidence to install the laser at Lick and then at Keck. And as people have been saying, today Keck really does lead the world in laser guide star adaptive optics. So a little bit of extragalactic science highlights. I just chose 2 of them. The first one is work that my group has been doing on identifying and measuring the masses of dual black holes in the cores of colliding galaxies. So that's a big mouthful. Most galaxies, single galaxies, have supermassive black holes in their cores. And when I say supermassive, I mean 10 to the 7th to 10 to the 9th, or even 10 to the 10th times the mass of the sun. And when these gas-rich galaxies merge, there should be a phase where there's active accretion of gas onto both of the black holes that have been pulled into this mess that became the galaxy merger. And so Keck Laser Guide Star Adaptive Optics with both NERC-2 and OSIRIS has allowed us to identify the 2 AGNs in these galaxy collisions. This is just 3 examples. The first one, and these circles are where the black holes is 2 gas-rich colliding galaxies at a low redshift, Z of 0.02. Then there's Markarian 273 slightly farther away, again 2 black holes that are both actively accreting. And finally, one at Z of 0.34, which I think is one of the farthest that have been observed by these methods. Then let's go and ask what happens about galaxies farther away. So can galaxies form spiral structure in the early universe at redshifts bigger than 2? So David Law and Alice Shapley and Chuck Seidel and their colleagues used OSIRIS to analyze a galaxy whose name is BX442 at a redshift of 2.18. And here it is. Here's a picture of it. It's actually a spiral galaxy. ground designed spiral structure, dynamically hot ionized gas. And so they analyzed with OSIRIS the kinematics of how the material in this galaxy was moving. And in this top image, the colors represent the velocity of the gas and stars towards us and away from us. So the stuff that's blue is moving towards us on one side of the galaxy. The stuff that's red is moving away from us on the other side of the galaxy. So this galaxy is clearly rotating and has large-scale structure. And when you subtract the large-scale motions, you see what's left is the motions that maintain the spiral arms in this large-scale spiral. So let's finish with the proposed next-generation adaptive optics system. We tried to make a science-driven design, and we chose a few key science areas where we needed this adaptive optics system to excel. And that includes the formation and evolution of galaxies, dark matter in our galaxy and beyond, testing general relativity in the galactic center, and solar system and exoplanetary systems, as you've just heard from Bruce. So, and then we derived what kind of new key science capabilities we had to have in this next generation system that would meet the goals of these science areas. And these were quantitative goals. So that's what I'm going to discuss next. Here, I just want to point out that many of these key science capabilities are ones that are pathfinders for what the 30-meter telescope adaptive optics system aims to do. And to the extent that we can explore their feasibility and how well they work in different situations, I think it'll be helpful for this bigger telescope as well. So the first thing is to make the point that next generation AO will change the AO observing experience at Keck. This is a graph that I have to explain a bit. These percents on the bottom are a figure of merit called the Strehl ratio. 100% Strehl ratio is a perfect correction. 5% Strehl ratio, you might not want to be there. So, and the vertical is just a histogram of how many times in your observing program you'll see a Strehl ratio, in this case of 15%, for example. And the red is data from Mike Liu's survey of brown dwarfs, and the green, or whatever color this is a model that we have for the current Keck 2 AO system. So this is the situation today, and these blue lines are the histogram from Monte Carlo simulations of what you're going to get with next generation adaptive optics. So there are two things to point out. One is the worst performance of NGAO is better than the best performance of our system today. That's good. And the mean is way higher, sort of 70, 75, or 80%. And as I'll show you, that happens over a much larger fraction of the sky than we have accessible today. So what are the key technology areas? One of them is, as I said, is excellent adaptive optics correction, and that's because we're putting multiple laser guide stars, these little yellow things are laser guide stars, and this blue thing is supposed to be your favorite galaxy. So in the science field, which is 40 arcseconds across, we're using multiple lasers, which lets us get rid of something called the cone effect and get significantly better images. The second is high sky coverage. So the sky coverage is limited by the ability to find a faint tip tilt star to stabilize that laser beam so your image doesn't move. And so the method is to have a much larger field than we have today, 120 arcseconds in diameter, where we'll use 3 tip tilt stars. And the reason we can do this is that each of these tip tilt stars will have its own small laser guide star AO system, much less ambitious than the main one, but enough to make each of these tip tilt stars determine the image motion much more exactly. And then high sensitivity for faint objects like distant universe galaxies. We want to be highly sensitive, so we're going to cool the AO system in order to reduce the kinds of thermal backgrounds that Ian was talking about. So this is just 2 examples of what it can do, what it will be able to do. So the first thing is to show you the improved sky coverage. This white box, first of all, this big square here is a picture of the sky in negative, so stars are black and the background is white. And the white box is one of several so-called deep fields which are being studied by all sorts of space telescopes and ground-based telescopes at a much higher depth than average places in the sky so that the faintest things in the universe can be seen in these restricted areas. And the left panel shows the Goods North field, and the circles are the places where we can do adaptive optics correction with our current laser. The color indicates the Strehl ratio. So the peak Strehl ratios within each of these circles are something like, I can't quite read that. What are they here? 20%-ish or so, this blue. So we're covering less than half of the deep field, and the best Strehl ratio that we're getting is 20%. Here's the next generation adaptive optics. First of all, we're covering a much higher fraction of the field. That's the high sky coverage part. But the other thing you should notice is that in the areas which we're covering, the Strehl ratios are more like 70% or 80% in the middle here, and even in the not so good regions, they're down at 40%, which is, as we said, is better than any of the corrections that we're seeing today in our current adaptive optics system. Finally, an interesting field that is very turbulent right now, sorry for the pun, is a test of dark matter theory. If you do a simulation on a computer of a galaxy, which is shown here, it ends up having many, many satellite galaxies. And we all know when you look at a real galaxy, it has satellites, but it's obviously completely different from the number of satellites that are predicted in these dark matter simulations. So the idea here is to use gravitational lensing to try and see satellites that we haven't been able to see before in distant galaxies. So here's the distant galaxy we want to look at. Here's a massive galaxy that happens to line up with the distant galaxy that's maybe partway between the distant galaxy and us on Earth. And because gravity tends to bend light, the distant galaxy is seen as a ring, an Einstein ring, around the intermediate galaxy. And here's the kind of thing that has been done at Keck. This is now Keck and Hubble together. This is Phil Marshall's image. Here's the Einstein ring, and here's the lensing galaxy. So it turns out, this is now the current Keck adaptive optics image of that galaxy. And into that image, in the model, has been put the intensity that you would see from a satellite galaxy if it were there. So what you want to do is you want to make a mathematical model of this lensing system and subtract the mathematical model from the actual image and try to see the galaxy, the satellite galaxy. But you can't quite convince yourself that this little blue thing is any different from all the noise that's in the rest of the difference between the observations and the model. And this is our effort to model what next generation AO will do with the same satellite galaxy. Now when you do the subtraction, the evidence for the satellite is quite clear and quite significant statistically. So I want to finish up with talking about the next 10 years of adaptive optics at Keck. Many of these things are underway right now. The first is, as Peter said, we're going to do near-infrared tip-tilt correction, and the Caltech group and the Keck group are working on that. That's in 2014. The Keck 2 laser is going to be launched from the center of the telescope instead of from the side, which is a significant improvement. A next-generation laser is coming to Keck 2. This is the Galactic Center again. This is a simulation of what it's like now. This is an observation of what it's like now. This is a simulation of what it will be like when that next-generation laser is put on. And this next-generation laser, the compact one that's 0.7 meters across, is exactly the laser that one would use for the next-generation adaptive optics system. So this is sort of Mod 1 going on Keck 2. Peter told you about these point spread function reconstruction projects that are going on. They're going on through this whole period, and the goal is to have them done by 2016. We would like to have a detailed design review for the next generation adaptive optics system in 2015, and we have successfully completed the preliminary design, and we're ready to start the detailed design as soon as funding is identified. So if that actually gets going in 2015, next generation AO, which is shown here, will be on the sky in 2020-ish. And we are deeply looking forward to that. And we think it'll really be a new era in this whole area of laser guide star adaptive optics astronomy. So finally, Keck is a leader in both adaptive optics and laser guide stars. I used to hesitate to say this. It sounded like we were pounding our chest, but when you look at the statistical metrics, which you can measure, how many papers, how many this, how many that, we are really the leader in this field. There's a large scientific productivity, wide demand by the users, a great variety in the kind of science that's being done, and the next generation AO is a very high priority for our future. Thank you.